There's a rock sitting in a laboratory on Earth that shouldn't exist. At least, not the way we found it. It's a piece of Mars, blasted into space by an ancient impact and captured by Earth's gravity millions of years later. Inside, scientists found a crystal smaller than a grain of sand, a zircon that formed 4.45 billion years ago, when Mars was barely 100 million years old. That alone would be remarkable. But here's the impossible part. Trapped in that crystal's atomic structure are signatures that only form in the presence of hot water. Not ice ets, not vapor. Liquid water flowing across a planet whose surface was supposed to be molten lava. Mars had oceans before it even finished forming. Then, in 2024, something equally strange happened. The Perseverance rover drilled into a rock in Jezero crater and found leopard spot patterns containing organic molecules alongside chemical signatures that, on Earth, are produced almost exclusively by living things. These patterns are 3.5 billion years old from a time when Mars should have already been dying. Two discoveries, 4 billion years apart, both pointing to the same conclusion. Mars was habitable far earlier than we thought possible, and that habitability lasted far longer than we ever imagined. But here's the question that keeps scientists awake at night. If Mars was wet for billions of years, warm enough for liquid water, and possibly teeming with microbial life, what happened? Where did an entire ocean's worth of water disappear to? And more importantly, what did we miss in between? Hello there, and welcome to Sleepable Science. I'm so glad you found your way here tonight. Let yourself settle in. Take a slow, deep breath. Feel the weight leave your shoulders. Tonight, we're traveling to a world that once looked remarkably like home. A world with rivers carving through highlands, with lakes filling ancient craters, with rain perhaps falling from clouded skies. A world that somehow lost it all and became the frozen, rust-colored desert we see today. Mars is not just our neighboring planet. It's a mystery story written in stone and ice. A detective novel where every crater, every dried riverbed, every chemical signature is a clue. And tonight, we'll follow those clues from the planet's violent birth through its golden age of water, to its slow transformation into the silent world that waits for us now. Some of what you'll hear may surprise you. Other facts might simply drift past like clouds. And that's perfectly fine. You don't need to remember everything. Just let the story carry you gently toward rest. If these peaceful explorations help you unwind, consider subscribing. It helps others find their way here too, one sleepy soul at a time. Now let's begin. Close your eyes if you'd like. Breathe slowly, and let's discover what Mars is trying to tell us. Mars began its life with a fatal flaw. It was born in the wrong neighborhood. About 4.5 billion years ago, as our young sun gathered strength, a disk of gas and dust swirled around it. Within this disk, particles began sticking together. Dust became pebbles. Pebbles became boulders. Boulders collided and merged into planetesimals, growing larger with each impact. This is how all the rocky planets formed: Earth, Venus, Mercury, and Mars. But Mars had terrible luck with its location. Jupiter, forming farther out, grew massive quickly. Its gravity acted like a cosmic vacuum cleaner, disrupting the supply of building material that should have fed Mars's growth. Recent models suggest Jupiter may have migrated inward early in the solar system's history before moving back outward, scattering debris and starving the young Mars of the material it needed. The result? Mars ended up with only about 11% of Earth's mass. If Earth is a basketball, Mars is barely a softball. This size difference seems small, but it determined everything about Mars's future. Its thin atmosphere, its weak magnetic field, its inability to hold onto water. Mars was doomed from the moment it formed. Or so we thought. Around 4 billion years ago, something massive struck Mars. an object roughly the size of Pluto, slammed into the northern hemisphere with such force that it created the Borealis Basin, a depression covering 40% of the planet's surface. This is one of the largest impact structures in the entire solar system, stretching 10,600 kilometers across. For decades, scientists assumed this impact was just another violent chapter in the early solar system's chaotic history. But recent computer simulations suggest something unexpected. This catastrophic collision may have actually helped Mars hold on to water. The impact excavated an enormous basin, essentially a perfect bowl, and may have triggered volcanic outgassing that replenished the atmosphere, even as solar wind tried to strip it away. The Borealis Basin, it turns out, might have been Mars's first ocean floor. This raises a fascinating possibility. What if Mars's small size wasn't the death sentence we thought it was? What if this planet, despite being undersized and gravitationally weak, managed to create the conditions for habitability through a combination of volcanic activity, favorable impacts, and sheer geological persistence? The evidence suggests exactly that. During the Noachian period, between 4.1 and 3.7 billion years ago, Mars was warm and wet. Valley networks carved by flowing water branch across the southern highlands like the river systems of Earth. Delta deposits show where rivers emptied into crater lakes. And most tellingly, the ancient zircon crystal I mentioned earlier proves that liquid water existed almost from the planet's very beginning. But water alone doesn't make a world habitable. You also need time. Time for chemistry to become complex, for molecules to organize, for life to find a foothold. Earth's earliest life appeared roughly 3.8 to 4 billion years ago, almost as soon as the planet cooled enough to have liquid water. If the same timeline held for Mars, then life could have emerged during the Noachian period, when both planets were young and wet. Here's the twist. Mars might have been habitable before Earth was. Think about that for a moment. While Earth was still being pummeled by massive impacts, while our planet's surface was molten and hostile, Mars, smaller, farther from the sun, cooling faster, may have already had stable liquid water and the chemical ingredients for life. If life did arise on Mars during this early window, it would predate Earth's biosphere, which means we might all be Martians. Stand on Mars today and look up. The sky glows a butterscotch tan during the day, colored by dust hanging in the thin air. At sunset, counterintuitively, it turns blue near the sun, the exact opposite of Earth's red sunsets. This color reversal is your first hint that something fundamental is different about Mars's atmosphere. The atmospheric pressure at Mars's surface averages just 600 pascals, less than 1% of Earth's sea level pressure. That's thinner than the air at Mount Everest's summit. You couldn't breathe it even if it contained oxygen, which it doesn't. The atmosphere is 95% carbon dioxide. But here's what puzzles scientists. Mars shouldn't have lost its atmosphere this completely. Isotope measurements tell a fascinating story. The ratio of deuterium, heavy hydrogen, to normal hydrogen in Mars's atmosphere is 5 to 6 times higher than it should be. This indicates that Mars once had much more water, but the lighter hydrogen atoms escaped to space over billions of years, leaving behind a higher concentration of heavier deuterium. Based on these ratios, some researchers estimate Mars may have had enough water to cover the entire planet in an ocean 100 to 1,500 meters deep. An ocean on Mars. Not speculation. This is based on measurable atmospheric chemistry. So, where did it all go? The answer lies in something Mars lost even before its water: its magnetic field. Around 4.1 to 4.2 billion years ago, Mars's global magnetic field shut down. We know this from magnetized rocks in the southern highlands that froze a record of the field into their minerals as they cooled. Younger rocks show no such magnetization. Something happened to Mars's core. It either cooled and solidified, or convection stopped, and the planetary dynamo that generated the magnetic field died. Without this protective shield, Mars became vulnerable to solar wind, a constant stream of charged particles from the Sun. NASA's MAVEN spacecraft, which has been monitoring Mars since 2014, has measured this atmospheric loss in real time. Roughly 100 grams of atmosphere escapes to space every second. That might not sound like much, but multiply it by 4 billion years, and you've lost an ocean of air. During solar storms, the loss accelerates dramatically when a powerful coronal mass ejection from the Sun reaches Mars. MAVEN has observed the atmospheric erosion rate increase by a factor of 10 or more. Early in solar system history, when the young Sun was more active and prone to violent outbursts, Mars may have been losing atmosphere far more rapidly. But here's where the story gets interesting. Mars didn't give up without a fight. The planet has something called crustal magnetic fields, localized patches of ancient magnetized rock, primarily in the southern highlands, that create mini magnetic umbrellas. These aren't strong enough to protect the whole planet, but they do shield the regions beneath them. Some scientists have proposed that life, if it exists on Mars today, might survive in these magnetically protected pockets where atmospheric loss is reduced. There's another surprise hiding in Mars's atmosphere. It breathes. During southern winter, temperatures drop so low that carbon dioxide freezes directly out of the air, forming a seasonal cap of dry ice at the pole. This removes 25 to 30% of the atmosphere's total mass, causing the global pressure to drop measurably. When summer returns and the dry ice sublimes back into gas, the pressure rises again. No other planet in the solar system experiences such dramatic seasonal atmospheric changes. And then there's the methane mystery. Methane shouldn't exist in Mars's atmosphere. Ultraviolet radiation from the Sun breaks down methane molecules in just a few hundred years. Yet the Curiosity rover has detected methane at Gale Crater. And stranger still, the concentrations vary seasonally, rising and falling in a repeating annual pattern. This indicates an active source replenishing the methane continuously. On Earth, about 90% of atmospheric methane comes from living organisms, bacteria in wetlands, cattle, termites. The remaining 10% comes from geological sources like volcanic outgassing or serpentinization, a chemical reaction between water and certain types of rock. Mars doesn't have active volcanoes, as far as we know, which leaves two possibilities. Either there's an unknown geological process producing methane, or something beneath the surface is alive and metabolizing. The measurements are real. The methane is there. What's producing it remains one of Mars's deepest mysteries. Now we come to something that defies belief, even though we can see it clearly from orbit. Olympus Mons, the largest volcano in the solar system. The numbers alone are staggering. The volcano rises 21.9 kilometers above the surrounding plains, more than twice the height of Mount Everest. But unlike Everest, which is part of a mountain range, Olympus Mons stands alone. A solitary mountain chasm, so massive that if you could somehow place it on Earth, it would cover the entire state of Arizona. The summit is so high, it protrudes above most of Mars's atmosphere. Standing at the peak, you'd experience only 12% of the already thin atmospheric pressure at Mars's surface. You'd be essentially in space, with stars visible even during the day. But here's what makes Olympus Mons truly remarkable. It grew at the same location for hundreds of millions of years, perhaps longer than 1 billion years. On Earth, this would be impossible. Our planet has plate tectonics. The crust moves. When a volcanic hotspot like the one beneath Hawaii erupts, it creates a volcano. But then the tectonic plate carries that volcano away from the hotspot, and a new volcano begins forming. This creates a chain of islands, each one progressively older as you move away from the active hotspot. Mars has no plate tectonics. its crust sits motionless over volcanic hotspots, allowing lava to erupt at the same location for geological eternity. Layer upon layer upon layer of solidified lava, building upward and outward, creating mountains that would collapse under their own weight on Earth but stand tall in Mars's weaker gravity, 38% of Earth's. The volcano summit holds another surprise: a complex caldera measuring 80 kilometers long and 60 kilometers wide, with a depth reaching 3.2 kilometers. This isn't a single crater, but multiple overlapping collapse features, suggesting Olympus Mons underwent several cycles of catastrophic eruption and collapse over its lifetime. When was the last eruption? Estimates for the youngest lava flows on Olympus Mons range from 25 to 2 million years ago, geologically recent. Some planetary scientists believe the volcano may not be extinct, but merely dormant, capable of erupting again if Mars's interior can generate enough heat. Which raises a tantalizing question. What if Olympus Mons were to erupt while humans were living on Mars? Would we see it as a natural disaster, or as confirmation that Mars is still geologically alive? There's one more mystery surrounding Olympus Mons: the basal escarpment, a cliff up to 8 kilometers high that rings the volcano's base like a gigantic wall. Scientists debate how this formed. The most accepted explanation involves massive landslides as the volcano's flanks collapsed under immense weight. But there's a more controversial idea. Some researchers have suggested the escarpment might represent an ancient shoreline. If true, this would mean Olympus Mons once stood as a volcanic island in a Martian ocean, with waves lapping at its base. The idea remains speculative and hotly debated, but recent computer models of ancient Martian oceans consistently place the water level at or near the elevation of the escarpment. Imagine that, a volcanic island larger than Arizona, rising from a northern ocean, under red skies lit by a younger sun. That's the Mars we lost. While Olympus Mons reaches toward space, another geological feature tears across Mars's face like a wound that never healed: Valles Marineris, the largest canyon system in the solar system. The numbers are difficult to grasp. The canyon stretches 4,000 kilometers from end to end, roughly the distance from Los Angeles to New York. In places, it plunges 7 kilometers deep, nearly 4 times the depth of the Grand Canyon. At its widest, the chasm yawns 200 kilometers from rim to rim. If you stood on one side, the opposite wall would be beyond the horizon. Unlike Earth's Grand Canyon, which was patiently carved by the Colorado River over millions of years, Valles Marineris formed through a combination of tectonic cracking and erosion. The canyon likely began when the Tharsis volcanic region, where Olympus Mons stands, bulged upward from the pressure of magma below. This uplift stretched and fractured the surrounding crust like skin pulled too tight. The initial fractures deepened over time through erosion. Water seepage, landslides, and wind-blown sand carved the canyons wider and deeper. Evidence of water is everywhere in Valles Marineris. Layered deposits on the canyon floor suggest ancient lakes may have filled parts of the system. Channel networks show where water once flowed from: the canyon walls. Some sections contain minerals that only form in the presence of liquid water. This wasn't just a dry crack in the crust. It was a watershed, a place where water collected, flowed, and perhaps created habitable environments for millions of years. The canyon's sheer walls reveal Mars's geological history, like the pages of a book. Different colored layers represent different periods: ancient volcanic flows, sedimentary deposits from standing water, wind-blown dust from drier times. By studying these layers from orbit, and eventually with rovers, scientists can reconstruct how Mars's climate changed over billions of years. But here's what makes Valles Marineris truly extraordinary. Parts of it may have been habitable relatively recently in geological terms. Some of the youngest mineral deposits, those containing evidence of water, could be as young as a few 100 million years old. While that sounds ancient, remember that Mars is 4.5 billion years old. A few million years ago is recent. Dinosaurs still walked Earth's surface just 65 million years ago. If water persisted in Valles Marineris long after the rest of Mars dried up, the canyon could have served as a refuge, the last place on Mars where surface life could have survived before retreating underground or going extinct. Future human missions will almost certainly explore Valles Marineris. The layered walls provide easy access to billions of years of geological history. The canyon's depth might offer protection from radiation. The atmosphere, thin as it is thicker at lower elevations, providing slightly more shielding. And if water ice exists in shadowed areas or beneath the surface, the canyon could provide resources for human settlements. Standing at the rim of Valles Marineris would be an experience unlike any on Earth. The canyon would stretch beyond the horizon in both directions. The far wall would be invisible, lost in haze and distance. The silence would be absolute. No water, no wind strong enough to hear. Just the thin whisper of Martian air moving through an empty wound in the planet's surface. Mars has two tiny companions in its journey around the sun, Phobos and Deimos. They're barely worthy of being called moons, irregularly shaped, dark, heavily cratered chunks of rock that look more like captured asteroids than proper satellites. Phobos, the larger, measures only 27 kilometers across at its widest. Deimos is even smaller at 12.6 kilometers. Both are among the darkest objects in the solar system, reflecting only about 6% of sunlight, darker than charcoal. But their small size and dark color hide a fascinating mystery. We don't know where they came from. The obvious answer seems to be captured asteroids. Their composition resembles carbonaceous chondrites, a type of asteroid rich in carbon. Their darkness matches. The asteroid belt lies relatively nearby in cosmic terms. Simple explanation, right? Not quite. Both Phobos and Deimos orbit almost perfectly in Mars's equatorial plane, following nearly circular paths. Capturing an asteroid typically produces a highly elliptical, tilted orbit, exactly the opposite of what we observe. To achieve Phobos and Deimos's current orbits through capture would require some mechanism to slow them down and circularize their paths, perhaps atmospheric drag over millions of years. But Mars's atmosphere has been thin for billions of years, probably too thin to significantly alter the orbits of objects as distant as Deimos. An alternative hypothesis suggests both moons formed from debris ejected by a massive impact on Mars, similar to how Earth's moon likely formed from a giant impact. Computer simulations published in 2021 showed this is possible. A large impactor strikes Mars, material is thrown into orbit, and instead of forming one large moon, the debris creates multiple smaller satellites, some of which eventually spiral back into Mars, while others, Phobos and Deimos, survive. This would make the moons much younger than Mars itself, perhaps only 1 to 2.7 billion years old. And it would explain their composition if the impactor happened to be carbonaceous in nature. Here's the unsettling part. Phobos is doomed, and we can calculate exactly how long it has left. Phobos orbits only 6,000 kilometers above Mars's surface, closer to its planet than any other known moon in the solar system. At this distance, it completes an orbit in just 7 hours and 39 minutes. From the Martian surface, you'd see Phobos rise in the west, race across the sky, and set in the east in just over 4 hours, the opposite direction of our moon's motion. But tidal forces from Mars are gradually slowing Phobos down, causing its orbit to decay. The moon is spiraling inward at a rate of about 1.8 meters per century. That doesn't sound fast, but the mathematics are inexorable. Within 30 to 50 million years, Phobos will either crash into Mars or, more likely, be torn apart by tidal forces as it crosses the Roche limit. When Phobos disintegrates, Mars will briefly have a ring system, a halo of debris encircling the planet like Saturn's rings, though far less spectacular. Over time, the ring particles will spiral down and impact the surface, adding Phobos' material to the Martian soil. Deimos, orbiting farther out at 23,000 kilometers, faces the opposite fate. Tidal forces are gradually pushing it away from Mars. Eventually, in perhaps hundreds of millions of years, Deimos may escape Mars's gravity entirely and become an independent asteroid orbiting the Sun. Asaph Hall discovered both moons in August 1877, naming them Phobos, fear, and Deimos, dread, after the sons of Ares, the Greek god of war. The names proved prophetic. Both moons are racing toward their destruction, one falling inward, one drifting away. Temporary companions to a planet that has already lost so much. Let's talk about the rock that started this whole journey, Cheyava Falls. In July 2024, the Perseverance rover examined this unremarkable-looking stone in Jezero crater and found something that made the science team catch their breath. The rock contains millimeter-sized spots arranged in a leopard pattern. Inside these spots, organic molecules. Surrounding them, minerals and chemical signatures that, on Earth, are almost exclusively associated with microbial life. The key phrase there is on Earth. Because that's the maddening thing about searching for life on Mars. Every biosignature we know how to recognize comes from studying Earth life. We're looking for Earth-like life using Earth-based assumptions. If Martian life exists and evolved independently, it might use completely different chemistry, different metabolic pathways, different molecular building blocks. Still, Cheyava Falls is tantalizing. The organic molecules are there, measured, confirmed, analyzed. The mineral patterns match what we see in rocks on Earth where microbes have altered their environment. The chemical energy sources that Earth microbes would use are present. But, and this is crucial, none of this proves life created these patterns. High temperatures from volcanic activity could potentially produce similar features. Chemical reactions between water and rock could create organic molecules without biology. The patterns could be coincidental, which is why NASA scientists emphasize Cheyava Falls is enigmatic. It's intriguing, it's worth studying further, but it's not proof of life. That determination will require returning the sample to Earth and analyzing it with instruments too large and complex to send to Mars. The sample return mission, currently planned for the early 2030s, will be humanity's most complex robotic space mission ever attempted. Multiple spacecraft, multiple launches, rendezvous in Mars orbit, safe return to Earth. If it succeeds, we'll finally be able to answer the question, did life ever exist on Mars? But there's a darker possibility that keeps astrobiologists awake at night. What if we're looking in the wrong place? Perseverance is exploring Jezero crater, an ancient lakebed from 3.5 billion years ago. By that time, Mars was already in decline. Its atmosphere thinning, its water disappearing. If life arose during the Noachian period when Mars was warm and wet, it would have had over 500 million years to evolve before conditions deteriorated. By the time Jezero's lake existed, Martian life might have already retreated underground, into aquifers and caves where liquid water could persist, protected from radiation and temperature extremes. If Martian life exists today, it's almost certainly underground. Surface conditions are too harsh, intense ultraviolet radiation, toxic perchlorate in the soil, temperatures that swing wildly, pressure too low for liquid water. But 100 meters down? A kilometer down? Conditions might be very different. Geothermal heat could keep water liquid. Rock layers would block radiation. Pressure would increase. We've barely scratched the surface. The deepest any rover has drilled is about 70 centimeters. The deepest planned drilling, Europe's Rosalind Franklin rover, will reach only 2 meters. Imagine if the only samples of Earth we'd ever examined came from drilling 2 meters into the Sahara Desert. Would we conclude Earth has no life? For all our telescopes and orbiters, our understanding of Mars truly transformed when we put wheels on the ground. The first rover to touch Martian soil was tiny, barely the size of a microwave oven. Sojourner landed in 1997 as part of the Mars Pathfinder mission, demonstrating that a mobile robot could actually work on another planet. It drove around for nearly 3 months, analyzing rocks and sending back images that captivated the world. Its mission was supposed to last a week. It survived for 12. But Sojourner was just the beginning. In January 2004, 2 golf cart-sized rovers, named Spirit and Opportunity, bounced to a landing on opposite sides of Mars, cocooned in airbags. They were designed to last 90 days. Spirit kept working for over 6 years. Opportunity, incredibly, operated for nearly 15 years, becoming one of the most successful robotic explorers in history. Opportunity's journey reads like an adventure novel. Landing in Meridiani Planum, the rover immediately found the evidence it was sent to discover: hematite blueberries, tiny spherical minerals that form only in the presence of water. Over the years, Opportunity drove more than 45 kilometers, a marathon across Martian terrain, examining ancient rocks, peering into craters, and discovering clear proof that liquid water once flowed across the surface. The rover even found a meteorite sitting on the surface, a chunk of iron nickel called heat shield rock. This discovery proved something scientists had theorized but never confirmed. Mars, like Earth, is occasionally struck by space debris. The meteorite had been sitting there for thousands of years, slowly oxidizing in the thin Martian air. Opportunity's end came in June 2018, when a planet-wide dust storm blocked out the sun. The rover's solar panels couldn't generate power. It sent a final transmission, essentially saying, "My battery is low, and it's getting dark," and went silent. Despite hundreds of attempts to re-establish contact over the following months, Opportunity never woke up. NASA officially declared the mission complete in February 2019. Somewhere in Mars's Perseverance Valley, covered in dust, the rover sits dormant, a monument to human curiosity. Meanwhile, Curiosity had been working since 2012, powered not by solar panels, but by a radioisotope thermoelectric generator, essentially a nuclear battery. This freed the rover from dependence on sunlight, allowing it to work through dust storms and Martian winters. Curiosity's mission is to climb Mount Sharp in Gale Crater, examining layered rocks that preserve different periods of Martian climate history. As the rover climbs higher, it literally travels forward through time, reading the geological record like a book. The rover has found clear evidence that Gale Crater once held a lake that persisted for millions of years, long enough, potentially, for life to emerge. Then in 2021 came Perseverance, bringing new capabilities and a new mission: collecting samples for eventual return to Earth. The rover carries 43 sample tubes, each one a pristine container waiting to be filled with carefully selected rocks and soil. As of early 2025, Perseverance has collected over 24 samples, each one sealed and cached for future retrieval. But Perseverance also brought a hitchhiker that changed everything: Ingenuity, a 1.8 kilogram helicopter designed to prove that powered flight is possible in Mars's thin atmosphere. Ingenuity was supposed to fly 5 times. Just 5. Prove the technology works and then stop. Instead, the little helicopter kept flying, and flying, and flying. By the time its mission ended in January 2024, due to rotor damage, Ingenuity had completed 72 flights, soaring as high as 24 meters, traveling several kilometers, and serving as a scout for Perseverance. Those 72 flights fundamentally changed how we think about Mars exploration. Future missions can now include aerial vehicles, drones that can explore cliffs, caves, and canyons inaccessible to wheeled rovers. We can search for water ice in shadowed craters. We can examine layered formations from multiple angles. The sky, thin as it is no longer the limit. China's Zhurong rover, which landed in 2021, added another dimension to Mars exploration. Operating in Utopia Planitia, Zhurong studied a different region than NASA's rovers, expanding our global understanding of Martian geology. Though the rover entered hibernation during the harsh Martian winter and may not wake again, its mission demonstrated that multiple nations can successfully explore Mars. Each rover has its own personality, its own story. Spirit died trying to climb a hill. Opportunity drove until the sun went dark. Curiosity climbs mountains and drills into time. Perseverance collects history in sample tubes. And ingenuity, little ingenuity, taught us how to fly on another world. These aren't just machines. There are ambassadors to Mars, our eyes and hands on a world we cannot yet reach ourselves. And every image they send back, every measurement they take, every discovery they make brings us one step closer to the day when human footprints will join their wheel tracks in the red dust. Here's something that doesn't get enough attention. Mars lost its water, but we know where a lot of it went. It's still there. The polar ice caps contain vast amounts of frozen water. The northern cap alone holds enough water ice to cover the entire planet in a layer 35 meters deep if melted. Ground-penetrating radar from the Mars Reconnaissance Orbiter has detected massive deposits of subsurface ice at high and mid-latitudes. Fresh meteor impacts occasionally punch through the soil and expose bright white ice lying just beneath the surface. When you add it all up, polar ice, subsurface ice, hydrated minerals in rocks, possible deep underground aquifers, Mars may still contain a significant fraction of its original water, not scattered to space, not chemically locked away forever, just frozen, waiting. This changes the question from where did the water go to why did Mars freeze? The answer involves a cascade of failures. The magnetic field died first, exposing the atmosphere to solar wind. As the atmosphere thinned, surface pressure dropped. Lower pressure meant water evaporated more easily or froze rather than staying liquid. Without large bodies of liquid water, the greenhouse effect weakened. Less greenhouse warming meant colder temperatures. Colder temperatures froze more water. A positive feedback loop driving Mars toward the frozen state we see today. But here's the fascinating part. This might be reversible. I'm not talking about full terraforming, turning Mars into Earth 2.0. That remains science fiction requiring technologies and resources we don't possess. But localized warming, creating habitable pockets, that might be achievable with technology we already have or could develop in the coming decades. Place a greenhouse dome over a patch of ice-rich soil. Add heat. The ice melts into liquid water. Plants could grow in Martian soil with the right nutrients added. The atmosphere inside the dome would be breathable. Humans could live there. Scale that up to a valley, then a crater, then multiple craters. Not transforming the entire planet, but creating an archipelago of habitable zones. Islands of green in a red desert. This isn't science fiction. This is engineering. Difficult engineering, certainly. Expensive engineering, absolutely. But possible engineering. Mars isn't dead. It's dormant. And dormancy, unlike death, is reversible. Mars and Earth are siblings, born from the same disk of dust and gas around a young sun. They started with similar raw materials, similar processes of formation. Yet they ended up radically different. One a thriving water world teeming with life, the other a frozen desert where silence reigns. The differences begin with size. Mars has only 11% of Earth's mass and about 38% of its surface gravity. If you weigh 70 kilograms on Earth, you'd weigh just 27 kilograms on Mars. This might sound liberating. Imagine how high you could jump. But weaker gravity creates fundamental problems for a planet trying to hold onto its atmosphere and water. The day length, though, is remarkably similar. A Martian day, called a sol, lasts 24 hours and 37 minutes, only slightly longer than Earth's 24-hour day. This similarity would make adapting to Martian time relatively easy for human settlers. Your biological clock wouldn't need much adjustment, but a Martian year is almost twice as long as Earth's, 687 Earth days compared to our 365. This happens because Mars orbits farther from the Sun, at an average distance of 228 million kilometers, compared to Earth's 150 million kilometers. The greater distance also means Mars receives only about 43% of the sunlight that reaches Earth. Both planets have seasons, caused by the tilt of their rotational axes. Earth tilts at 23.4 degrees, Mars at 25 degrees, remarkably close. But Martian seasons are longer and more extreme because of the planet's elliptical orbit and its greater distance from the Sun. When Mars is closest to the Sun, the southern hemisphere experiences a short, intense summer. When it's farthest away, southern winter lasts longer and is bitterly cold. Temperature differences between the two worlds are stark. Earth's average surface temperature hovers around 15 degrees Celsius, comfortable enough that liquid water exists in abundance. Mars averages negative 60 degrees Celsius, though it can range from a relatively balmy 20 degrees at the equator in summer to a brutal negative 125 degrees at the poles in winter. Both planets have polar ice caps, but with a crucial difference. Earth's poles are pure water ice. Mars's poles contain both water ice and frozen carbon dioxide, dry ice. The southern polar cap is permanently covered with a layer of frozen CO2 about 8 meters thick, sitting atop water ice below. Here's a surprising fact. If you could drain Earth's oceans, the remaining dry land would be roughly equal in surface area to all of Mars. This makes Mars, in a sense, a more accessible world for exploration. No vast seas to cross, no deep oceans blocking access to large portions of the surface. The most profound difference lies underground. Earth has a churning molten iron core that generates a powerful magnetic field, protecting our planet from solar wind and helping retain our atmosphere. Mars's core cooled and solidified billions of years ago, or at least stopped convecting efficiently. The magnetic field died, leaving Mars vulnerable. But both planets preserve memories of their past in different ways. On Earth, plate tectonics recycles the crust, erasing ancient history. The oldest rocks on our surface are only about 4 billion years old and quite rare. Most of Earth's crust is younger than a few 100 million years. Mars has no plate tectonics. Its surface is a palimpsest, a written record going back over 4 billion years, perfectly preserved. The valley networks carved during the Noachian period still look fresh. Impact craters from the solar system's violent youth still mark the highlands. When we study Mars, we're reading a history book Earth lost long ago. Understanding why these two sister planets diverge so dramatically is one of planetary science's great questions. If we can figure out what killed Mars, what transformed a warm, wet world into a frozen desert, we might better understand the delicate balance that keeps Earth habitable. Because climate can change, magnetic fields can fail, atmospheres can be lost. Mars is a warning written in stone and ice, but it's also a testament to planetary resilience. Despite losing its magnetic field, despite losing most of its atmosphere, despite freezing solid, Mars still holds vast amounts of water. The planet isn't dead, it's dormant. And dormancy, unlike extinction, can potentially be reversed. The story we've been telling tonight, of ancient rivers and lost oceans, of atmospheric stripping and frozen poles, is not finished. Mars continues to teach us, and humanity is only beginning to learn. The most ambitious robotic mission currently planned is the Mars Sample Return Campaign, scheduled for the early 2030s. This international effort will involve multiple spacecraft, multiple launches, and a level of complexity never before attempted in planetary exploration. A lander will collect the sample tubes. Perseverance has been caching, load them into a small rocket, and launch them into Mars orbit. An orbiter will capture these samples and return them to Earth for analysis in laboratories with instruments too large and sophisticated to send to Mars. These samples could finally answer the question, did life ever exist on Mars? Beyond sample return, other missions loom on the horizon. Europe's delayed Rosalind Franklin rover will eventually drill up to 2 meters beneath the surface, deeper than any previous mission, searching for organic molecules protected from radiation. Japan's MMX mission will visit Phobos and return samples from the tiny moon's surface, possibly capturing material that was blasted off Mars by ancient impacts. But the ultimate goal, the dream that drives much of this exploration, is sending humans to Mars. NASA has outlined plans for crewed missions in the late 2030s or early 2040s. SpaceX proposes even more ambitious timelines with its Starship vehicle. China has announced long-term human Mars exploration goals. The timeline remains uncertain, the challenge is immense, but the momentum is building. A human mission to Mars represents humanity's greatest technical challenge yet. The journey alone would take 6 to 9 months each way, depending on planetary alignment. Astronauts would spend that time in a confined spacecraft, exposed to cosmic radiation and microgravity, both of which pose serious health risks. Bones weaken, muscles atrophy. Radiation increases cancer risk. Once on Mars, the challenges multiply. The thin atmosphere provides almost no protection from radiation or micrometeorites. Temperatures swing wildly. Dust storms can last for months. A punctured spacesuit means instant death. The low pressure would cause water in your blood to vaporize in seconds. Yet these challenges are solvable with existing or near-term technology. Spacecraft can be designed with radiation shielding. Habitats can be buried beneath Martian soil for protection. Water ice can be mined and melted. The MOXIE experiment aboard Perseverance has already demonstrated that oxygen can be extracted from Mars's carbon dioxide atmosphere, about 6 to 8 grams per hour, enough for one person to breathe for about 15 minutes. That doesn't sound like much, but scale it up, run it continuously, and you can support human life. You can also split water into hydrogen and oxygen, producing rocket fuel for the return journey. You can grow food in greenhouses using Martian soil, supplemented with nutrients and fertilizers brought from Earth or extracted from minerals. The first Mars missions won't be permanent colonies. They'll be more like Antarctic research stations, small crews conducting science, testing technologies, searching for resources, then returning home. But over time, these outposts might expand. Temporary shelters could become permanent habitats. Small crews could become larger communities. Some visionaries dream even bigger, terraforming Mars, transforming the entire planet into an Earth-like world with a breathable atmosphere and liquid water on the surface. Ideas include releasing greenhouse gases to warm the planet, importing volatiles from comets, or using massive orbital mirrors to focus sunlight on the ice caps. These proposals remain firmly in the realm of science fiction. The technology required is centuries away, if it's possible at all. The ethical questions are profound. Do we have the right to fundamentally alter another world? What if Martian life exists and we destroy it in our attempt to create Earth 2.0? More realistic near-term goals involve creating habitable pockets, domed craters, sheltered valleys, underground settlements. Not transforming the entire planet, but creating an archipelago of green zones in a red desert. Islands of life on a world that once hosted oceans. The first person to walk on Mars is probably alive today, somewhere on Earth. They might be a child watching videos of perseverance and ingenuity, dreaming of red skies. They might be an engineering student designing better spacesuits or more efficient propulsion systems. They might be someone who hasn't yet realized that space exploration is their calling. But they're out there. And when they finally set foot on Martian soil, dusty red ground beneath their boots, butterscotch sky overhead, Olympus Mons rising on the horizon, they'll be completing a journey that started with ancient humans looking up at a wandering red light and wondering what it was. Mars has waited 4.5 billion years for this moment. It can wait a few more decades. As we drift back from Mars tonight, let one final thought settle with you. Mars is a time machine. Every rock on its surface, every grain of sand, every ice crystal at the poles contains a record of the planet's history. Mars has no plate tectonics to recycle its crust, no weathering rain to erode the evidence, no oceans to bury the past beneath sediment. This ancient surface remains, perfectly preserved, waiting to tell its story to anyone patient enough to listen. The valley networks carved by rivers 3.8 billion years ago still look fresh. The impact craters from the solar system's violent youth still mark the southern highlands. The lava flows from Olympus Mons' last eruption, perhaps only 2 million years ago, lie undisturbed. On Earth, plate tectonics and erosion erase the past. The oldest rocks on our planet's surface date back only 4 billion years, and they're rare. Most of Earth's crust is younger than a few hundred million years. We've lost our planet's first billion years of history. But Mars remembers. Mars has kept the receipts. Every chapter of planetary evolution, from molten formation to watery prime to frozen present, is written in Martian stone. When humans finally walk on Mars, they won't just be exploring another world. They'll be walking through our solar system's history book, reading chapters Earth has long forgotten. And who knows? Somewhere in those ancient rocks, preserved in a dried lakebed or sealed in a collapsed lava tube, we might find the answer to humanity's deepest question. Are we alone? If life arose independently on two planets orbiting the same star, it means life isn't rare. It means the universe might be filled with living worlds, each one writing its own story in stone and ice and ancient water. Mars is still writing, still waiting, still holding its secrets close, and we're finally learning to read them. If this journey has brought you peace or sparked your curiosity, consider subscribing. It helps others find their way here too, one sleepy soul at a time. Sleep well. Dream of red deserts and ancient rivers, of leopard-spotted rocks and frozen moons, of a world that once was and might one day be again. The stars are patient. Mars will wait.